Hi, today we're going through the paper from 2012 looking at question 18. So in question 18 we're given these two circuits here. In the first part we're asked to complete circuit A so it can record the current and voltage across the resistor and then to work out how big this current actually is. We're told the resistor has 2 kilo ohms, so we'll just label that on. Okay, so let's start. So we know that an ammeter must be placed in series with the component over which it's measuring the current. So let's do that. Let's put the ammeter in series with our resistor and our voltage. And we know similarly that the voltmeter must be in parallel. So let's connect that parallel across our resistor. And that's the circuit completed. It then asks us to evaluate the current in the circuit. Well, we know that voltage is current times resistance, which implies that our current is V over R. Well, that's simply 12 over 2000, which comes out to 6 milliamps. We're now asked to sketch the current time dependence from when this switch in B is moved to position E, i.e. the capacitor is being charged. And we're asked to estimate the time capital T for when the current isn't changing very much. We're then asked to sketch the current time dependence, current time behaviour, from this point, from when the current isn't changing very much, if the switch is moved to D, i.e. asked to sketch the discharge pattern. So let's start by sketching the current time dependence for when the switch is moved to E. Okay, well, we know that charge is going to move from the voltage supply, round here. So current's going to flow. And there's going to be a build-up of charge on this capacitor. So the current is going to slowly decrease, was going to exponentially decrease, until essentially none flows. So let's sketch that down. So what that means is we're going to have on a current time current, and put this in milliamps and this in seconds. Well, we know it starts at 6 milliamps, and it's going to come down in an exponential decay as the charge builds up at the capacitor and stops the flow of charge. So it goes 10 down towards exponentially towards 0. And after some time capital T, the time doesn't change very much. Now, a good rule of thumb is that the time T, capital T, after which the current doesn't change very much, it's approximately equal to 5 tau, where tau is the time constant of the circuit, which is the resistance of the circuit times the capacitance. Well, in that case, we have our resistance is 2000 ohms times the capacitance, which is 4 microfarads. That's 4 times 10 to the minus 6. Well, that gives you 8,000 times 10 to the minus 6, which equals to 8 times 10 to the minus 3. So that gives us that our time t is approximately equal to 5 times that, 40 times 10 to the minus 3, or 4 times 10 to the minus 2 seconds, which is equal to 40 milliseconds. Okay, well now we're asked to sketch the current time behaviour from this point if the switch is moved to D. Well, what's going to happen now is the charge, there was a build-up of positive charge on this capacitor on this side here. Well, now when it's connected to D, there's nothing to drive the charge. It's going to simply flow back the other way, so we're going to have the reverse. So we're going to sketch that down. We have the exact opposite of our other graph. So it's going to be time here in seconds and our current here in milliamps. And it's going to start this time from minus 6 milliamps. And it's going to come up in a very similar patterns before and come up like so, and tends like this. That's going to be the answer.